Welcome to the 2025 AP Chemistry Free Response Question Answers. We are going to go through these one at a time and get an opportunity to take a look at each individual question, explore a little bit about what each question is being asked, and how we can easily go through and try to solve some of these problems to the best of our ability. So in just providing a brief overview of the exam, looked to be a little more challenging this year than in previous years. That's not necessarily a bad thing, just an opportunity to explore more in different realms of chemistry. So, again, really excited to bring that to you today. So I guess without further ado, we're just going to go ahead and dive in. I'll probably make some segues in between each of the different questions so I can divide this up into separate videos if people want to watch it that way. Or if you want to watch it as just one whole big video, I'll probably post that as well. But again, these are just my thoughts, my opinions on the exam. Really haven't had an opportunity to look at any answer keys or anything like that, because obviously this is literally the day it's been posted. It's posted, maybe 3 or 4 hours ago? So I'm not sure if anything's been posted yet, but again, we're just going to kind of dive in and take a look here. So as we scroll down, taking a look at what we've got here, just kind of our standard AP Chemistry fodder. Let's get to the questions here. So here we go. We're going to start with question number 1. It says, answer the following questions about magnesium. An incomplete mass spectrum for magnesium is shown in the diagram, and it says the percent abundance is 79%. So get our little pointer here. The percent abundance of the other two natural isotopes of magnesium, 25 and 26, are approximately equal. Okay. So it says complete the mass spectrum in part A by drawing thick lines in appropriate locations to represent the percent abundance of magnesium 25 and magnesium 26. All right, so it does say here that it's 79%. So that's good to start us off with. It says that 25 and 26 are approximately equal. So if we do a little bit of math here and take 100 minus 79, get that in my calculator, that's 21. I know that, but I'm still going to punch it in my calculator anyways. So we get 21% that's left over that's split between 25 and 26. So we're going to divide that by 2. So each of these should have 10.5% relative abundance. So if I draw this in the graph here, that's probably a little bit too big, but 10.5% right there. Erase a little bit of that first one. No, I'll just erase the whole thing. So again, 10.5%, perfect. Okay, so awesome. We're off to a really, really good start. It says describe the difference in atomic structure that accounts for the difference in mass between magnesium 25 and magnesium 26. Well, they're both magnesium, so that indicates that they have the same number of protons. So we have 12 positively charged protons here and 12 positively protons here. So the difference in atomic structure that's going to account for the difference in mass is the number of neutrons, in which case magnesium 25 contains 13 neutrons, and in which magnesium 26 contains 14 neutrons. So that is going to account for the difference. So pretty easy mass spec graph to start us off. Let's see what we've got coming up next here. All right, so it says a student prepares a 1.85 times 10 to the negative third molar solution of MgNO3 in beaker 1 and a 2.80 times 10 to the negative fourth molar solution of NaOH in beaker 2 as shown. The particle diagram shown represents a magnesium ion in a beaker. A sodium ion in beaker 2 has a weaker attraction to water than Mg2+ does. Explain this phenomenon using Coulomb's law and each of the following. So we're going to use Coulomb's law to discuss the relative charge of the ions. Well, again, I'm not going to provide a full-length explanation written out for each of these, but we know that Mg has a 2+ charge, and Na has a 1+ charge. And so remember that the magnitude of charge is directly correlated to the strength of the attraction of the ion to the water molecules. So in this case, magnesium has a 2+ charge, and so therefore would have a stronger attraction due to the fact it is a 2+ charge when compared to sodium, which is only a 1+ charge. So that takes into account the relative charge of the ions that are present in the solution. How about the relative radii of the ions? Well, if we take a look at what's going on a molecular level, I'm going to go ahead and erase these here. We know that magnesium has 12 protons in its nucleus and sodium has 11 protons in its nucleus. And so this part of the question has to do with the relative nuclear charge. Both of these actually have the same number of electrons in their structure because they are both ions. So as a result, the strength of attraction to the water molecules is directly correlated to the number of positively charged protons in the nucleus or nuclear charge. So because sodium has a weaker nuclear charge, that is, it only has 11 protons in the nucleus when compared to magnesium, which has 12, this is going to have a weaker attraction to the water molecules, again, due to the fact that it has a smaller nuclear charge and has less attraction, of course, due to Coulomb's law, opposite charges attract. And the greater the magnitude of charge, the greater attraction, as well as the smaller the radius of the ion here. So this is going to have a much smaller radius due to the fact that the outermost electrons are going to be more attracted to the nucleus due to it having 12 protons. So this has a greater nuclear charge, and so as a result, its atomic radius is smaller. And we know that smaller ions tend to have greater attraction to water molecules through ion dipole intermolecular forces. So, takes care of that question. Let's take a look at the next one we got here. We have, it's asked us to calculate the pH of the solution in beaker 2. So we have a 2.8 times 10 to the negative 4th molar NaOH solution. So 2.80 times 10 to the negative 4th. Again, that's a molar solution there. So because this is a strong base, I can take the negative log of this concentration. So negative log of 2.80 times 10 to the negative 4th. That will actually give me the pOH of the solution. And remember, we can take 14 minus the pOH to get the pH of this solution. So we'll take the negative log of, so negative log 2.8 times 10 to the negative 4th. And what I get is a pOH that is 3.55. And again, if we subtract that from 14, we will get the pH of our solution. So 14 minus the 3.55 gives me a pH of 10.45. Okay, so there's the first couple of questions done. Let's see what we got up next. Nothing too difficult here. Nice little introduction. All right, so for part D here, it says a student combines 35.00 milliliters of a 1.85 times 10 to the negative 3rd molar MgNO32 solution with 50 milliliters of 2.80 times 10 to the negative 4th NaOH, as shown in the diagram. It wants us to calculate the Mg after the two solutions are combined, but before any reaction takes place, and assume that the volumes are additive. So in order to actually go through and calculate the concentration of magnesium after the solution has been added, we need to know two pieces of information. We need to know the total number of moles of magnesium over the total volume of the solution. So if we're adding 50 milliliters of solution with 35 milliliters, we know our total volume is going to be 85.0 milliliters, or, because we're asked to calculate the concentration, 0.085 liters. In order to get the magnesium, we're going to have to get the magnesium out of this MgNO32 here. So in order to solve for the moles of magnesium, we are going to take our molarity here, 1.85 times 10 to the negative 3rd, set that equal to our molarity. Remember, molarity is moles over liters, so 0.035 liters. And we'll solve for x here. Now, the moles of MgNO3 and moles of Mg are in a 1-to-1 mole ratio, so whatever we solve for on top of this molarity calculation is going to be the same as the number of moles of Mg in the solution. So we're going to take 0.035. We're going to multiply that by 1.85 times 10 to the negative 3rd. And what we end up with is 6.48 times 10 to the negative 5th. And then we're just going to simply divide that out and get our new concentration of magnesium in the solution. So we're going to divide that, 6.48 times 10 to the negative 5th. And we're going to divide that by 0.085 liters to get our new concentration of Mg. And our new concentration of Mg is 7.62 times 10 to the negative 4th. And that is molarity of Mg2+. All right? So again, fairly straightforward there. Let's move on and see what we have for the next problem. Just scroll down here. All right, so it looks like we have a solubility equilibria question here. It says the dissolution of magnesium hydroxide is represented by the following equation, and you're given a KSP value. It says write the expression for KSP. So let's do that first. So part I here, KSP is equal to, remember, anytime we do equilibrium, it's products over reactants and coefficients become exponents. So it's going to be Mg2+ times OH minus, and then we are going to square that because of that coefficient there. It says, after the two solutions are combined in beaker 3 as described in part D, but before any reaction takes place, the OH minus is 1.65 times 10 to the negative fourth. Using your answer in part D, calculate the value of the reaction quotient. So in this case, we're not going to be solving for K. We're actually given the value for K, but we're going to be solving for Q. And it appears in the next question, we're going to be comparing Q and K in order to figure out if a precipitate is formed. So let's get some pieces of information here. Remember, we solve for Q the same way we solve for K. The only difference is that Q is when we're not at equilibrium yet, and then we can utilize that information in order to figure out what direction the reaction goes in order to reestablish chemical equilibrium. So we're going to go ahead and plug in our OH minus. Our Mg actually comes from part D, so I'm going to scroll back up to the top here. It's at 7.62 times 10 to the negative fourth, so we're going to plug that in here. So 7.62 times 10 to the negative fourth. And then what we're going to do is we're going to quantitatively go ahead and solve for Q. So let's plug that into our calculator. So we're going to take 1.65 times 10 to the negative fourth. We are going to square that. Then we're going to multiply that by 7.62 times 10 to the negative fourth. And I get a value that is 2.07. So 2.07 times 10 to the negative 11th. Okay, so there's our value for the reaction quotient Q. And then it says using Q and K, determine whether a precipitate forms. So the first thing we need to do is look at the values for Q and K and figure out which one is bigger. So when we compare Q and K, Q is bigger than K. And a couple ways to look at this. You can just memorize this, but what I like to do is I like to tell my students to go ahead and follow the mouth. If we follow the mouth, that means that the reaction is going to shift towards our reactants in order to achieve equilibrium, and we're shifting towards our solid. And so because Q is greater than K, the reaction is going to shift towards our reactants, which is where the solid is. And so as a result, the answer is yes, we are going to form a precipitate as a result of this. All right. The last question here says that in a separate experiment, the student adds HNO3 to decrease the pH of a saturated solution. Does the amount of undissolved MgOH2 increase, decrease, or remain the same? So if we think about this from an equilibrium standpoint, I'm going to go and get rid of this information up here. Adding in HNO3 is a strong acid, and so that contributes a lot of H3O plus to our solution. Well, what H3O plus does when it reacts with the OH minus here is it neutralizes it to produce water, and so as a result, that drops the OH minus concentration. When it drops the OH minus concentration, Q no longer equals K. The system then responds by shifting to the right in order to reestablish chemical equilibrium. And so as a result, more of the solid is going to become aqueous ions. So when I read the question again, it says, does the amount of undissolved MgOH2 increase, decrease, or remain the same? Well, the amount of undissolved is going to decrease because when we add in HNO3, it's a strong acid, generates H3O plus ions, it neutralizes the OH minus, decreasing the OH minus concentration. When that happens, Q no longer equals K, and the system responds by shifting right to reestablish equilibrium. Thus, more of the undissolved MgOH2 will become dissolved. So as a result, it will decrease. I think that might be it for question 1. Okay, question 1 in the books. It is done. We only have 6 more questions left, and we are finished. So let's go ahead and move to question 2. If you just saw question 1, that's all you want to see. Stop the video right here. Thanks for watching. We'll see you next time. Question 2, let's move on. All right, it says, answer the following questions about ascorbic acid. Okay, so we have an acid question here. Student combusts a sample of ascorbic acid to determine its chemical composition. The only products of the reaction are 0.2400 molar CO2 and 2.883 grams of H2O. And it says, calculate the moles of H2O produced. So that's a simple calculation we can do. So let's take 2.883 grams of H2O, and we're going to use the molar mass, 18.02, and we're going to go ahead and convert that to moles. So let's plug that into our calculator. So 2.883, divide that by 18.02, and we get 0.159, so we're going to round that actually to 0.1600 moles of H2O. All right, part 2 here says the mole ratio of carbon to oxygen is 1:1 in ascorbic acid. Based on the information in the answer to part A, determine the empirical formula. So we have our information that the moles of carbon to moles of oxygen in ascorbic acid is 1:1. So what that's telling me is that if I have 0.2400 moles of CO2, that means I have 0.2400 moles of carbon, 0.2400 moles of oxygen. And then here, I have my moles of water, but what I need to take into consideration is that there are 2 hydrogens for every 1 H2O. And so this ends up being 0.3200 moles of hydrogen. So if I were to move forward with the empirical formula, I wish I had room. That's the only thing I wish I had more of in these questions is I don't have any room to write, and it's frustrating. I'm going to go ahead and get rid of these little markings here. Okay. And I'm going to go ahead and put the 0.3200 moles of hydrogen here. So we have all of our mole values. So remember that when we do empirical formula, we divide by the smallest mole number. So we're going to divide by the 0.24 for each of these. So we end up with carbon 1, oxygen 1, and hydrogen 0.32 divided by 0.24, 1.33. And so because not all of these are equal to 1, we're going to go ahead and need to multiply all of these to get the appropriate empirical formula. 1.33, the least common multiple of that to give a whole number is 3. So we're going to take all these values and multiply them by 3. So what I end up with for my empirical formula is C3H4O3. I don't think it really matters here exactly what order you put them in. Obviously, if it's an acid, most often the hydrogen comes first, but it just tells me to put it in this order here. So that's exactly what I'm going to do and what I'm going to leave it as. So yeah, that's what we're going to do, and I'm quite content with that. So it says here, ascorbic acid acts as a weak acid, as shown in the following equation, and it says the following titration curve was produced when 10 milliliters sample of ascorbic acid was titrated using 0.055 molar NaOH. And it says here to calculate the molar concentration of the ascorbic acid solution. So this is just going to be find the equivalence point and utilize the M1V1 equals M2V2 in order to be able to solve for this. So the equivalence point's right here at 16 milliliters. So what that tells me is that the concentration of acid, which we'll call M1, we use 10 milliliters of it, so 10.0, equals the concentration of the base, so 0.0550, multiplied by the volume of base that's added, which is 16 milliliters. So if I go through that and algebraically solve for M1, I should get my answer, 0.0550 times 16. And we're going to divide that by 10. So what I end up with is a molar concentration of 0.088 of the ascorbic acid solution. We'll abbreviate that HASC just like it does here. All right, let's see what we got next. So it says next to determine the pKa of ascorbic acid. So in order to solve for the pKa of the ascorbic acid, remember that pH equals pKa at the half equivalence point. The half equivalence point, the equivalence point is at 16. The half equivalence point's at 8. So right here, this is where your pH equals your pKa. And so it looks to be about 4.1 for the pKa value. And then lastly, it says, what is the value of the ratio of base to acid? So this is a Henderson-Hasselbalch equation when the pH of the solution is 4.7. If the pH of the solution is 4.7 and the pKa is 4.1, we know that when we add that to the log of the concentration of the base over the acid, we can just algebraically solve for this pretty easily. So subtracting these values, we get 0.6 equals the log of the concentration of base over acid. And so we're going to take 10 to the 0.6 power to get the ratio of base over acid. Simple enough, because 10 to the power of is the inverse function of the log. So 10 raised to the 0.6 gives me 3.98 is the ratio of base to acid, which makes sense because if we go back and actually look at the graph, right? It tells us that the pH of the solution we're looking at is 4.7. Well, that is well beyond the half equivalence point, which tells me that I should have a higher concentration of base than I would of my acid, right? Because 4.7 would be here. And that pH is indicating that the concentration of the ascorbic acid is less than that of the base. Okay, so the base should be in a higher amount, and that is verified by this calculation down here below. So pretty straightforward. Okay, let's keep moving on. Dehydroascorbic acid can be produced by reacting ascorbic acid with triiodide ion as represented in the following equation. The student runs 3 trials of the reaction with different initial concentration of HASC and I3-, producing the following data. And so we're given 3 different trials here with different initial concentrations and different rates of formation. It says here for number 1 that the rate law for the reaction looks like it appears to be first order for both of them. It says explain how the data in the table supports the conclusion that the reaction is first order with respect to HASC. So we're only doing one of these. So that's quite nice. Remember that when we do this, we need to find 2 reactions. One where HASC changes, but the other one does not. So we're going to be looking at experiments 1 and 3 here because I3 does not change, but HASC does. The concentration of HASC changes by a factor of 2. And when I look at the rate also changes by a factor of 2. If you can't visualize that by seeing these 2 numbers, take the bigger number and divide it by the smaller number. So 4.914 times 10 to the negative 4th divided by 2.5457 times 10 to the negative 4th. And when we divide these values, we get 2. And remember that reaction order is exponential based. So we always ask ourselves this question when we get to this 2 to what power is 2? And the answer is 1. So using that as your justification, that is indicative of a first order reaction. The next part asks us to go through and calculate the value for K for the reaction, include units with your answer. So we'll just pick the first reaction here. We're just going to plug in the values for trial 1 into the rate expression here and solve for the value for K. So 2.457 times 10 to the negative 4th equals K times 0.450 times 1.200. Sorry, ran out of room. And now all we do is we just algebraically solve for the value for K here. So let's take 2.457 times 10 to the negative 4th, divide that by 0.450, and divide that by 1.20. And our value for K is 4.55 times 10 to the negative 4th. I always stress, make sure you include your proper units, and anytime you calculate the rate constant, it is always 1 over the unit for seconds, and since it was molarity per second, it's 1 over second for this. Next question. The triiodide ion is significantly more soluble in water than elemental iodine is. Identify an intermolecular force between I3 and water that is not present between I2 and water that could explain the difference in solubility. So if we just kind of break each of these down, I2 is a nonpolar molecule, right? Something bonded to itself, so it only has London dispersion forces. I3-, however, is a little bit trickier to deal with. We don't talk a lot about, at least I don't talk a lot about expanded octets here, but this is actually another nonpolar molecule. It is linear. I know it looks a little strange with those 3 lone pairs surrounding that central atom, but it is a nonpolar molecule and would only exhibit London dispersion forces. However, this is an ion, and so as a result, the predominant intermolecular force that we're looking at here is actually the ion dipole force that exists between the I3 molecule and water, because it will be attracted to the hydrogens that are in water. So finding a lot of questions about intermolecular forces and water solubility with this particular AP exam. We had one at the very beginning when we talked about magnesium and sodium and whatnot, but you see another one that pops up here. So quite interesting to take a look at. So that's it for question 2. So if you just came to see question 2, thank you so much, and we will see you very, very soon. All right, moving on to question number 3. Question 3 says that white phosphorus is composed of P4 molecules with a tetrahedral structure as shown in the diagram on the left. Each P atom is bonded to the other 3 P atoms by single bonds as shown in the incomplete Lewis diagram on the right. And it says here in the box in part A, complete the Lewis diagram by drawing non-bonding electrons. So This should be pretty simple. We got 4 molecules of phosphorus. Each phosphorus brings 5 valence electrons to the party. So there's 20 total valence electrons to play with. If we count each bond as a pair, so that's 2, 4, 6, 8, 10, 12. So that tells me that 12 electrons are already taken by the bonds that are here. And we're left with 8. And since there are 4 phosphoruses, each one is going to get a lone pair of electrons. Cool. That's pretty straightforward. Let's see what we got for part B. So the reaction of white phosphorus with oxygen to form P4O10 is thermodynamically favorable. Okay, so that means we have a negative value for delta G. And the reaction is represented by equation 1. The entropy change for the reaction is negative using particle level reasoning. Explain why entropy decreases as the reaction progresses. So delta S is negative, indicating we're getting more order as the reaction takes place. Well, if I take a look at the nature of my elements and of themselves, we start off with a solid and 5 molecules of gas, or sorry, 5 moles of gas, and we end up with a solid. So a couple ways to look at this. We have a state of matter of gas that is being converted into a state of matter of solid, which again is more orderly. We can also look at the fact that we have 6 moles on the left-hand side of our equation and 1 mole on the right-hand side. So that is an indication of more order as well. So some combination of both of those is probably the best answer choice for this particular response, indicating that there's more order because we're taking 5 moles of gas and converting them into 1 mole of solid. And in addition to that, we have 6 total moles on the left side of the equation on our reactant side and 1 mole on the right-hand side. So some indication of that is a way to tell that we are increasing in order or decreasing disorder by the delta S being negative. Additionally, it says the enthalpy change for the reaction delta H is also negative. The student claims that the favorability of the reaction is driven by enthalpy and not by entropy. Is the student's claim correct? Justify your answer by using the relationship between delta G, delta H, and delta S. So delta G is negative, delta H is negative, and delta S is negative. So if we kind of put just signs in for our equation, because in this we're going to use our delta G equals delta H minus T delta S. We're not going to do any mathematical calculations with this, but let's see what we get here. So delta G is negative, delta H is negative, and T delta S is also negative. So if we break this down a little bit more, we're essentially trying to figure out what is causing delta G to be negative in this equation. So if I go through and analyze this, right, delta H is a negative value. If I subtract the negative from that, that's essentially like adding a positive. So a negative value for delta S is not contributing to the negative value for delta G. So the student is correct. This negative delta H value is what is making delta G negative. A negative value for delta S does not contribute to the thermodynamic favorability of the reaction. In fact, it does the opposite. And in fact, the positive nature of T delta S here actually makes the reaction less thermodynamically favorable. So when it says the reaction is driven by enthalpy, the student is absolutely 100% correct. P4O10 reacts exothermically with water to produce phosphoric acid as represented by this reaction. A chemist uses a calorimetry experiment to determine the enthalpy change for a reaction as represented in the following diagram. Chemist carries out the calorimetry experiment and records the following information. So, looks like we're trying to solve for Q here. Out of heat released during the experiment. So remember, anytime we do a calorimetry experiment, we always want to focus on the water that's here. I did not mean to make that yellow because that no longer looks like water. But we focus on the water in the experiment. So when we do this, we're going to be focusing on using Q equals MC delta T, of course. Mass of H2O, our initial and final changes in temperature. And, so this is the specific heat of water. So we can just solve for this pretty easily. So Q equals M, so 100. Specific heat, 4.18. And delta T, so the final temperature is 22.38 minus 22.00. All right, and then we'll be able to just simply algebraically solve for Q. So 100 times 0.418 times, 100 times 4.18 times 0.38, because that's the difference in temperature. And so we end up with the Q value here of 159 joules. Now it does say to convert it to kilojoules. So just divide that by 1,000. So 0.159 kilojoules. Okay. So now that we've done that, it asks us to calculate the delta H for the reaction and include the sign in your answer. So remember that the amount of Q that is gained by the surroundings is equal to the Q that is lost by the system. So we need to flip the sign for Q. So that's going to be negative 0.159 kilojoules. So all we need to do now is take the 0.1 grams of P4O10 and convert that to moles, and then we're going to divide our kilojoules by that mole value, and that should give us the enthalpy for the reaction. So 0.100 grams of P4O10. I'm going to need to get the molar mass of this. Find that on my handy dandy periodic table. Let me try to figure that out real quick. So 283.88. When I solve for moles, I get 3.52 times 10 to the negative fourth. We're just going to take that mole value and we're going to move that down here. So what we end up with is 0.159 kilojoules divided by 3.52 times 10 to the negative fourth moles, and I will get my enthalpy change. And I get a value that is negative 452 kilojoules per mole. So again, pretty straightforward question. We had something very similar last year. Solve for the value for Q. Make sure you go through and flip the sign for Q because we're focusing on the reaction, not the surroundings. And then remember to divide by your mole value to get your final enthalpy. All right, let's go ahead and read out part D here. It says the chemist weighed out 0.100 grams of P4O10. I definitely feel like there's a typo there. Weighed out 0.100 grams P4O10 of, and 100 grams of H2O to perform a second trial. In the second trial, given some of the P4O10 stuck to the weighing paper and was not transferred to the calorimeter. Given the P4O10 is the limiting reactant, would delta T for the second trial be greater than, less than, or equal to the value in the first trial, and justify your answer? Well, if that's the case, then the amount of grams of P4O10 that actually reacted is actually less than what we would expect. And so because we have less grams that are reacting, we're going to end up having a temperature change that is less than what is expected. And if the temperature change is less than what is expected, oh, that's just simply it. I thought they were going to ask about enthalpy change, but no, it says, would the delta T for the second trial be greater than, less than, or equal to that of the first trial? Well, it's going to be less. If we have less grams of P4O10 react, then that means that the amount of grams reacted, as we discussed, is going to be less. And so the amount of enthalpy change as a result of that reaction is going to be less as well. So yeah, pretty straightforward there. As the P4 also reacts readily with Cl2 to produce phosphorus trichloride, which in turn reacts with Cl2 in the equilibrium process to produce PCl5. Reactions are represented below by equations 3 and 4. And it says to calculate the standard enthalpy change of PCl5 given this equation. Okay, so we have a Hess's law type equation here. Ooh. This one's a little bit tricky. We got a lot of fractions that are here, so it makes this a little more challenging. So it looks to me like this first equation here is going to have to get divided by 4 in order to produce the right value here. So that ends up with 1/4 P4. It ends up with a PCl3 as well. I also notice that I need to keep PCl5 on the right side and cancel out the PCl3 on the left. So I think this is going to end up working out for us in the end here if we divide this by 4 and keep this value the same. So we're going to take negative 1148, divide that by 4, so negative 287, and then I'm going to add to that negative 88 with enthalpy values. When you do Hess's law, you just simply add them together. So negative 287 plus negative 88 gives us negative 375 kilojoules per mole. Awesome. So let's keep moving on. Scroll down here. Gives us a particle level diagram of a vessel at equilibrium mixture at 546 Kelvin according to the fourth equation. And it gives us an equation here and a delta H value. It says if each particle in the diagram represents partial pressure of 1 atm, what is the value of Kp? Okay, so let's go ahead and write our expression for Kp. Again, products over reactants, so it's the partial pressure of PCl5 over the product of the partial pressure of PCl3 times the partial pressure of Cl2. And so if we just count up the particles here, we got 1, 2, 3, 4. So that's going to go on top. We have 1, 2 down at the bottom, and then 1, 2, 3, 4, 5, 6. So we end up with a Kp value that is 4 over 12, which is 0.33. Seems simple enough. Okay, let's move forward. It says, does the value for K increase, decrease, or remain the same when temperature is increased? So if we do take a look at the value for K here, remember K, the equilibrium constant, only changes with a change in temperature. So we are going to experience a change here. Delta H is negative. So the way I go through and remember this is if delta H is negative, heat is being released. And so we're going to treat heat as a product. And so if the K value, if the delta H is negative value and temperatures increase, we again treat heat like a reactant or product. So if we were to think Le Chatelier's principle here, we're going to shift to the left. And if we shift to the left, that tells us that we end up with more reactants at equilibrium. So the K value here is actually going to decrease as a result of this. The reaction is exothermic, and increasing the temperature of an exothermic reaction results in a decrease in the value for the equilibrium constant K. So I think that wraps up question number 3 here, which is awesome. We're making really good progress and really good time through this. If you're done with question 3, then have a great day. We'll see you soon. If not, let's move on to the short free response questions. Let's move on to question 4. All right, says a scientist is investigating properties of a mixture of, it looks like methanol and H2CO. The scientist generates the following diagram to represent the mixture. First thing says to identify the hybridization of the valence orbitals of C in the H2CO molecule. So if we take a look here, the steric number for that is 3, meaning that we have 3 atoms and lone pairs attached to that central atom, and that corresponds directly with an sp2 hybridization. Nice entry question there. In the diagram provided, draw a single dashed line to represent a strong hydrogen bonding attraction between one CH3OH molecule and one H2CO molecule. Now, I find that interesting because I'm always under the impression that hydrogen bonding has to occur between 2 molecules that have an oxygen that's, of 2 molecules that a hydrogen is covalently bonded to an oxygen, nitrogen, or fluorine here. And apparently they're not under the assumption of that. I need to always go back and maybe refresh that a little bit. But, I mean, anything where I would say this oxygen, maybe right here, is attracted to this hydrogen, that could potentially be representative of a hydrogen bond. There's multiple ways to go through and show that. I think as long as you have this particular oxygen here that's covalently bonded to the hydrogen of the other molecule, I think you're in good shape here. It's difficult to say because, again, I'm always under the assumption that you have to have 2 molecules where a hydrogen is covalently bonded to an oxygen, nitrogen, or fluorine, and then show the hydrogen bonding in between the 2 different molecules. But I suppose I could be wrong. So I'll leave it there. And if you think different, then hey, by all means, let me know. I'm always curious to learn more about my craft. Part C here says a scientist plans to cool a gaseous mixture to form a liquid mixture and finds data on 2 compounds, and the data is summarized in the table. It says propose a temperature in which the mixture should be cooled such that CH3OH and H2CO will both be liquid. So you're given a melting point here. So anything beyond this is a liquid. Anything below this is a liquid for the boiling point. So really anything that, I guess, corresponds to being in between both these values and these values. So I'm just going to say 185, but really I think there's a variety of different temperatures that you could give here. Very, very easy point if you're paying very close attention. It Second part says the scientist analyzes the mixture after it is cooled and determines that 8.59 grams of the methanol is present. Calculate the amount of thermal energy that was removed to condense at its boiling point. Okay, so energy removed, so that implies that we're going to have a positive value here. Right, because removal implies that it gives the negative sign here. We're taking out that energy. I want to know how much energy is removed, so positive sign here. So 8.59 grams of the methanol gives you the molar mass, which is nice, 32.04 grams per 1 mole. And it gives us the enthalpy of vaporization here. So that is going to be 1 mole is 37.6 kilojoules. So just do a little bit of math here. So 8.59 divided by 32.04 times 37.6. So I end up with 10.1 kilojoules being removed. I always like to include that word there because that implies we're taking it out in order to condense it at its boiling point. So we're going from a gas to a liquid. We're taking out that amount of kilojoules of energy. So very nice. Okay, so that was question number 4. Pretty straightforward again. I like these types of questions. I feel like it's very fair. There's lots of easy entry points to these, but there are also some tricky questions as well. So I kind of like the mix that we got going on here. It's nice. It's nice. Let's move on to question 5. It says complete Lewis diagrams and some physical properties for compounds are given. So again, let's go through and analyze this. It says based on Vesper theory, predict the geometry around the Si atom. 4 atoms and no lone pairs. My goodness, that is tetrahedral at its finest. Simple enough. A student claims that compound Y has a higher boiling point than compound X because compound Y has stronger London dispersion forces. Do you agree or disagree? If I look at these molecules, they all share similar intermolecular forces. You've got a similar structure, really. The only difference here in the structure is the carbon and the silicon. And so the answer to this is going to be yes. These share similar intermolecular forces. The only difference is that silicon is a larger molecule, and so therefore we would say that compound Y has a larger polarizable electron cloud. And so therefore would have stronger London dispersion forces and as a result have a higher boiling point. Easy way to check this is that silicon has a larger molar mass, it's a larger molecule, it has more electrons, so therefore has a larger polarizable electron cloud and greater London dispersion forces. So I would wholeheartedly agree with that statement. An equimolar mixture of the 2 compounds is heated. When the mixture reaches 82 degrees Celsius, which compound will have the higher vapor pressure? So higher vapor pressure just implies that there's going to be more molecules of gas of that particular compound at that temperature. Because compound X has a boiling point at 82 degrees Celsius, that tells me that this is going to be more readily become a gas at 82 degrees Celsius, and therefore would have more gas at 82 degrees Celsius. And so as a result, because it's going to have more molecules of gas, it will exert the higher vapor pressure. So we're going to say compound X for the aforementioned reasons that it boils at 82 degrees Celsius. And because it boils at 82 degrees Celsius, it will more readily become a gas than compound Y. And as a result, have more gas molecules and have a higher vapor pressure. The mixture is heated to 198 degrees Celsius in a sealed, rigid 12.5 liter container, at which point both gases and the total pressure is 2.3. Calculate the number of moles of gas particles. So this is just a straight up PV equals nRT question. So we're given our pressure, so 2.30. Our volume, which is given as 12.5 liters. We're going to solve for moles. R value, 0.08206. And our temperature needs to be converted to Kelvin, so we're going to take 198 plus 273.15, and that gives us 471.15. So now we just need to algebraically solve for moles. So 2.3 times 12.5 divided by 0.08206 divided by 471.15. That gives us our mole value of 0.744 moles of gas. And just like that, I believe we have finished question number 5. Yes, we're getting towards the end here. Kind of sad. This is always an exciting day for me, but we'll move on to question number 6. So if you're done, have a good day. If not, let's move on to 6. Scientist constructs a galvanic cell as shown in the diagram. The cell operates, the zinc electrode increases in mass, and the aluminum electrode decreases in mass. A data table with the standard reduction potentials is shown down below. So we give it our voltage, which is nice. And first it says, write out the half reaction for the oxidation that occurs at the anode. So here we have a higher value on our standard reduction chart. So this is actually going to be what is being reduced. So this is our cathode. This is what's being oxidized. And so this is our anode. So it just wants the half reaction. So all I think it wants us to do is to just flip this equation. So we're going to have aluminum as a solid, Al, 3 plus, that's aqueous, and 3 electrons. Interesting entry question, pretty straightforward here. It says write the balanced net ionic equation for the overall reaction. So we need to make sure that we combine these two reactions. Remember that when you combine half reactions, you need to make sure that the moles of electrons cancel in them. So we need to take this equation, multiply by 3. This equation multiplied by 2. Remember that this equation is also the one that is flipped. So when we write this out, we're going to have 3 Zn, 2 plus, that's aqueous, plus 2 aluminum, that's solid, arrow, 2 aluminum, 3 plus, that's aqueous, and 3 solid zincs. Okay, so there's the full overall reaction here. It says initially, each electrode has a mass of 50 grams. When the cell is allowed to run for a period of time and is then stopped, which electrode's mass changed the most? And justify with the calculation. Okay, I've not seen anything quite like this before, so this is an interesting question. Okay. I mean, I already know the answer by looking at it, but it says justify it with the calculation. I'm going to lose 2 moles of aluminum and gain 3 moles of zinc. Molar mass of aluminum is 26.98, whereas zinc's is, give me a second, 65.38. So I already know based off of this information that I'm losing an extra mole of zinc and its molar mass is larger. So I know zinc is the right answer here, is going to be what changes the most, but calculating it, I think I could do this. Let's say we start off with losing 5 grams of aluminum, right? We lose aluminum in this process, correct? Yeah, aluminum decreases in mass. So if we lose 5 grams of aluminum, I bet I can do a molar conversion here. So 26.98 grams to 1 mole of aluminum. Let's use the mole ratio here. So 2 moles of aluminum to 3 moles of zinc. And then 1 mole of zinc, 65.38 grams. So I bet if I do it this way, I can show that for every 5 grams of aluminum that react, I produce so many grams of zinc. And as a result, I can prove that the zincs will change more. So if I calculate this, so 5 divided by 26.98 times 3 divided by 2 times 65.38, 18 grams of zinc. So I think that proves it with the calculation. If you have another way of doing it, let me know. I'm curious. But for every 5 grams of aluminum that react, 18 grams of zinc is produced. So I think that tells me that zinc changes more. And yeah, I think that answers the question. At least I hope it answers the question. I'm sure there's a different way to do it. It's just kind of the first thing that popped into my head. I have not seen anything like that before. So quite interesting. All right, so we're given a bunch of other half reactions here. Let's see what it says. It says the standard zinc aluminum cell has a voltage of 0.9. The scientist needs a galvanic cell that produces a greater voltage. The scientist has access to the chemical systems in the table. And I want to create, using zinc, so we're using this, what is the maximum voltage that could be generated under standard conditions? So I'm going to go ahead and eliminate a couple of these. Basically, it's either going to be the one at the top or the one at the bottom. That's kind of how this always works here. So if I use Be, we keep negative 0.76, but this beryllium gets flipped to 1.85. So if I use beryllium here, I end up with 1.09 volts. If I use gold, we keep the 1.50, but we flip the zinc. So 0.76. So 1.5 plus 0.76 gives me a voltage of 2.26 volts. So our winner here is gold, because that will produce a voltage of 2.26 volts. Yeah, all right. Pretty tame voltaic cell question. Don't mind that by any means. So really, really well done. Again, good entry point here, some good questions. I think this C part is going to throw some people for a loop because I don't know. It's not something that I explicitly cover, so I'm curious to see what my students come up with. But again, we'll just have to kind of wait and see how this turns out. So that's the end of part 6. Let's move on to the last and final question. Always a sad time when we get to the final question of the year. All right, answer the following questions about the glycolate ion, which acts as a base in aqueous solution. And we're given a Lewis diagram. It says, on the Lewis diagram, part A, circle the atom that accepts the proton from when the glycolate ion reacts with water. So in a very similar vein last year, we were asked to circle the hydrogen that's going to be donated. And as we know, this part of the molecule here tends to be the part where the hydrogen gets donated. So I'm going to make the assumption that it's the same part that it's going to accept the hydrogen. That's that COOH group that's present here. We can see here that you have a formal charge here of 0. Here, this formal charge is not accurate, or at least this formal charge is not 0. So to me, this is kind of begging for that hydrogen to be attached here to that oxygen to form, again, that carboxylic acid, that COOH group. It is quite important in the AP chemistry concept. So I'm going to go with that oxygen that's there. Move down here, it says when the glycolate ion reacts with water, it forms glycolic acid in the following expression. And the Kb expression is provided, which is great. So the first thing it asks us to do is at 25 degrees Celsius, 2.5 molar solution produces an OH minus of 1.3 times 10 to the negative fifth. And it asks us to calculate Kb. So, okay, so this is kind of like a modified version of a Rice table to solve for the equilibrium constant here. So Kb equals our glycolate, 2.5, so that's going to be going down here at the bottom. And then we have our OH minus concentration. Remember when you build a Rice table with us, this part here is plus X, especially when we deal with acids and bases. This part here is also plus X. So what that tells me is that the OH minus concentration is the same as the concentration of the glycolic acid. So when we plug this in, we're going to take 1.3 times 10 to the negative fifth. We're going to square it because, again, it's X and X on top here, so it ends up being X squared. And we're just going to go ahead and solve for Kb that way. So 1.3 times 10 to the negative fifth, square that value, and divide it by 2.5. So what I get here for Kb is 6.8 times 10 to the negative 11th. So that's calculated. Part 2 here says, using the answer to part B, calculate the Ka. That's easy enough. If I go and look at my formula sheet, 1.00 times 10 to the negative 14th equals Ka times Kb. So I'm just going to take 1 times 10 to the negative 14th. I'm going to divide that by 6.8 times 10 to the negative 11th. And I end up with a value of 1.5. Ka is 1.5 times 10 to the negative fourth. So again, just utilize your formula sheet and you shouldn't run into any issues with this. So awesome. Okay, let's keep moving on here. Last one, I think. Yes, last question. Oh, so sad. Glycolic acid can be produced from the hydrolysis of methyl glycolate A proposed mechanism for the reaction is given, and it says a student claims that H3O plus is a catalyst for the reaction. Do you agree or disagree? Well, H3O plus appears in step 1, and we get it back out in step number 2. That is the literal definition of a catalyst in a reaction mechanism. So I would wholeheartedly agree, because H3O plus appears in the first step, and then we get it back out in a subsequent step. So what that tells me is it's used and participates in the chemical reaction. It is not found in the overall balanced chemical equation. We do have an intermediate that's here as well, but this is the literal definition of a catalyst in a reaction mechanism. It starts one step and comes out a second step. So I would wholeheartedly agree with that. So I think that rounds it up. Pretty much everything here. So overall, I think this exam is a little more challenging than what we had last year. For sure. I think there's some easy entry points. I think there are definitely some challenging questions that are here that are going to require a little bit of thought. But overall, it's still pretty tame compared to some exams that I've seen previously. I like it. I like the variety that's in it. I think the variety is a little bit different. I think there is lots of different variety of questions that are here that I really, really enjoyed going through. And I hope you enjoyed going through it as well. So again, those are my thoughts on the 2025 AP Chemistry exam for this year. I hope you enjoyed it. And if you did, feel free to leave a like, feel free to subscribe, do what you need to do, all the fun YouTube stuff. All right, we'll see you guys next time. Thank you so much, and we'll see you very soon in the future. Bye, everybody.